Good morning or afternoon or evening to everyone, and thank you very much for joining me today in this coffee corner about Adina and the new possibilities that it brings to STAAD.Pro users. My name is Juan Trueba. I am Adina application engineer at Bentley. That is a slightly younger version of me. But I have nearly 16 years of professional experience as a structural and mechanical engineer with a background in finite element analysis. I'm chartered engineer in the United Kingdom, and I am certified as professional simulation engineer with NAFEMS Association. Right, so because this is the first coffee corner about Adina, it is going to be a bit general. We're going to be touching on many aspects, even though I will be showing certainly a number of small demos, examples, and illustrations. So this is the agenda for this coffee corner today. Some of you do have experience with Adina, but it will be new to most of you. So I'm going to give a very quick overview and talk about how things are changing now that Adina is part of Bentley systems. Then I will move on to presenting some of the key workflows of ways of leveraging Adina, in particular that STAAD.Pro to Adina workflow that is now available since STAAD version 23, which was very recently released. And after that, I will be showing specific features and applications that may be of interest, like nonlinear time history analysis, structural collapse, blast analysis, stage construction analysis, or cable stage structures too, just to mention a few. And at the end, I will show one last demo on how to perform nonlinear vacuum analysis, also using the STAAD to Adina workflow. So let me start with a very quick introduction to Adina. Adina is a very powerful and versatile finite element analysis program, originally founded by Professor Klaus-Jürgen Batze, who happens to be a civil engineer and was a professor at the MIT on mechanical engineering. These are some of the key modules available in Adina: structures, heat transfer, computational fluid dynamics, and also a combination of the three above. So if, for instance, we want to perform fire analysis on a structure, we can combine the structures with the thermal module. So Bentley acquired Adina last year with the aim to bring together the best of both worlds, the existing Bentley structural ecosystem and those extra advanced analysis capabilities that now we have available with Adina. New workflows are starting to come out right now, including some for STAAD.Pro, RAM elements, and also SACs. But of course, these are the first versions that have this possibility. And the idea is to continue to develop this workflow. So what you're going to see today doesn't stop here. And just to close up this chapter quite quickly, Adina has historically been used across many sectors and industries. So for more than 30 years, the software has been in constant development and been a pioneer in many areas. And the learning has been transferred and shared across sectors and disciplines. But we can expect to see now an acceleration in the infrastructure sector with a focus on civil structures, energy, traditional renewables, and water and wastewater. Those to the right are some examples from real-life projects, but of course there are many more, and I'm going to show you some applications today. So the question we're trying to answer here is how to make the most of that advanced analysis capability in Adina while maximizing the efficiency. So Adina can be used and continues to be used in different ways, but here we're going to concentrate in three key aspects. The first one and newest is the ability to import STAAD.Pro models into Adina to perform advanced analysis. I will talk about and give this. I will talk about this and give some details in a moment. The second one is the ability to start to modify models from the Adina user interface, and I'm also going to be covering this in a demo that I will play in a moment. And the third one is the ability to create or edit Adina input file. This Adina input file is a text file quite similar to the STAAD.Pro STD file that I'm sure you're familiar with, and I will expand on that as well. So let's start with the first one of the workflows, the ability to import models from STAAD. Those are examples from automatic exports from STAAD into Adina. As you can see, we can do this for 1D elements, whether beams, trusses, cables, and 2D elements like slabs or walls. On the example to the left, Adina allows us to capture the true cable behavior for static or dynamic analysis. On the example to the right, on that slab, imagine that you want to use compression-only springs for a dynamic analysis. Those are just some examples. So let me show you an entire workflow before we progress too much with presentation on how to import a model from STAAD into Adina. This video is going to take under 4 minutes, around 3.5 minutes, and we go all the way from this screen to performing a seismic time history analysis in Adina. So on the STAAD.Pro model, through File, Export, Import, we now have a command button. This is a new option with version 23, which allows to export that model to Adina. I chose to swap the vertical axis to have Z as my vertical axis in Adina. And this is the Adina user interface that you see in here. So we locate that input file that we've just created, and the model has been transferred over pretty much instantly: geometry, cross-sections, materials, supports, and so on. I'm going to run an implicit analysis of the structure, dynamic analysis of the structure subject to an earthquake excitation. So I'm going to define a series of time steps, 800 time steps, 20 milliseconds each, giving us a total solution time of 16 seconds. I need to apply the earthquake seismic excitation. So this is going to be a mass proportional loading. I want to define this on the X horizontal direction, so that vector is 1, 0, 0. And I want to multiply the mass of the structure by the signature of the earthquake. So I'm going to define a time function, just as you see on the screen. Thankfully, I can import CSV files or text files, and we can graph to see that is the signature of the earthquake. That is the time function that is going to multiply to my structure's mass. Finally, for a dynamic analysis, we need to apply some damping. So going to apply some Rayleigh damping coefficients. I have some pre-calculated values. And well, we are pretty much ready to solve this analysis. There is 800 time steps to be solved. I'm not going to show all of them, so I fast forwarded a little bit. We can see that it's taking 1 minute and 6 seconds to solve all 800 time steps in Adina. So it's quite fast actually. And now we can change to the post-processing screen, open the results files that we've just created. We can customize background colors and my structure elements colors. And in this particular case, I'm interested to see the deformed shape of the structure. So I'm going to use a magnification factor to the deformed shape of 10. Now we can better see the deformed shape of the structure, how it responds to that earthquake excitation. And finally, I'm going to create a small animation, an AVI file. This step is actually takes a little bit, few seconds longer because, well, we have to process, so Adina actually has to process 800 time steps. But that should be ready. And we just need to locate that file in our folder and, well, we can visualize it. Of course, we could have interrogated other results like forces and moments diagrams. We can graph results. We can export tabulated format to spreadsheets and so on, but it's not the aim of this particular demonstration. So just as a recap, it took literally seconds to export the model from STAAD into Adina. It took under 2 minutes to prepare the dynamic analysis. It took 1 minute and 6 seconds actually to solve that analysis, and we spent another minute or so in visualizing the results, so it's quite quick. The second workflow is the ability to use Adina as a standalone application and start or modify models from the Adina user interface. So if you have something like the structure to the left and you are used to using STAAD.Pro, we've seen that we have a workflow that is pretty much automatic, but of course we can use Adina as a traditional finite element package, and it has fairly capable options to create volumetric geometries like that tensile specimen or that column subject to blast. If you're not familiar with our Bentley structural channel on YouTube, we now have an Adina structures playlist, and the first video is that getting started with Adina that gives a good overview of the interface. So I recommend you to watch that video and others in the playlist. And finally, we have the Adina input file, which, as I said before, we have a text file that contains all the commands required to perform tasks in Adina, from simple operations like applying a load to the creation of an entire model. As I said before, this is like the similar to the STAAD.Pro STD file, even though it has its own commands, of course, different to the STAAD.Pro commands. It is a file that is accessible, that can be viewed and edited at any time, and is relatively easy to understand. There is a manual that explains what each command is, but we can also record operations, or we can actually create a model on the Adina user interface and save it as input file to find out those commands. Of course, this opens the doors to automation and scripting of the Adina input file, and as such, opportunity to automate the creation of models in Adina. I'm going to show you this example, which is a task that I had recently, where I want a model of a pressure vessel that I wanted to evaluate different geometry sizes and mesh distributions. So I wrote a very simple macro in Excel that took me, around half an hour to prepare. I'm not a coder by any means. And I'm not going to show the code behind this macro, but I'm going to show you how it works to give you an idea of its power and its possibilities. So that's the geometry to the right, and those are the geometry and mesh control parameters that I identified to that I wanted to tweak or play with. So I run the macro, and that has written a Adina input file for me that I can readily input, open from Adina, and that is the main body of the pressure vessel and that nozzle that is connected to it. And quite critically, I'm controlling the mesh around it, around that intersection, which is what I'm interested in. I'm going to close this model, go back to the macro. I'm going to tweak some of those geometry and mesh parameters. So it's a bigger vessel this time. The nozzle is not going to be eccentric, it's right at the middle. And I'm going to tweak the mesh density to something finer. I run the macro again. I go to File, Open Batch once again, and a new input file has been created just a minute after the previous one, and the model is now much bigger, so it takes a little bit longer to upload. But there it is. We have a bigger pressure vessel, at least certainly the body, and the nozzle in the center, and I'm controlling the mesh just as I want it. Of course, we can apply this to any kind of a structure. Here, for completeness, I'm showing you the entire pressure vessel, complete with supports, loading, materials, and so on. I could have automated all this, but I didn't have to. But as I was saying, we can apply these principles to any kind of a structure, whether it's a building, a bridge, a dam, it doesn't really matter. Okay, so having spoken about and visualized the workflows, let's now start to get a bit more specific what analysis we can do in Adina. And one important thing to discuss is that for all previously seen workflows, these are the modules and options that we have available. So we have a structures module, as I said at the beginning, we have a thermal module, and we have the computational fluid dynamics module. Today I'm going to focus on the structures module to the left-hand side of the screen. And I wanted to bring your attention to the bottom of that list. It says simplified fluids, the potential-based fluid elements that I will be presenting in a moment, which are different to the computational fluid dynamics, the CFD that you see at the bottom right of the screen. So these are fluid elements available within the structures module, and we will see how they are useful to model, for instance, liquid-filled tanks subject to earthquake excitations or dams and reservoirs, and so on. We will get there in a moment. Right, so in terms of now focusing on structures, in terms of basic analysis, those are well, certainly some of the things we can do in Adina. We have linear and nonlinear static analysis, implicit and explicit dynamics, model analysis to work out the frequencies and modes of a structure, model superposition, which allows us to obtain the dynamic response as a combination of the modes of vibration of the structure, and linearized backplane, which that linear backplane analysis is like the Euler backplane load, if you remember from college or university. And if somebody wants to do a nonlinear static analysis, a nonlinear backplane analysis, what we do is we call a nonlinear static analysis, and we probably need large displacements or nonlinear material properties. So I will show an example of nonlinear backplane analysis at the end of the presentation, and you will see that it's a static nonlinear. Adina offers us as well the possibility to automatically switch from one analysis type to another one. An example could be when we want to initialize the static conditions before we perform a dynamic analysis. Or for instance, if we have a cable state structure and we want to stress those cables, and that will affect dynamic behavior. So we want to run a static analysis first, nonlinear, and then a dynamic analysis. We can choose to switch when to switch from one analysis type to another one. And Adina also gives us the opportunity to automatically change if one model doesn't converge. For instance, a dynamic implicit analysis doesn't converge, we change to explicit dynamics automatically. And now we're going to list just a few structure analysis features, and I'm going to be showing after the slides animations and examples on all of those. So we now have available to the already great capabilities in STAAD.Pro. We have some additional possibilities now, like nonlinear time history analysis, nonlinear backplane, progressive failure and collapse, stage construction analysis, soil structure traction, or that simplified fluid that I mentioned before. And we also have additional element types and things that we can do that perhaps in STAAD, this means an enhancement for STAAD.Pro users. So let's start with a series of descriptions and animations on various of those features available in Adina. And the first one that I wanted to introduce is collapse analysis, which is an analysis type that we may want to analyze statically up to the point where the structure starts to see really large displacements. For those cases, Adina has the low-speed dynamics feature, which is a special technique developed to overcome convergence difficulties in collapse, post-collapse, and certain contact problems. So in general, we're talking about those problems that are difficult to converge. We have post-backplane behavior, large plasticity, complex contact conditions. So this is useful, for instance, to evaluate structures redundancy, the ability of the structure to form alternative load paths when a member fails. This could be because we're suddenly missing a column or in the event of fire. There is different scenarios. The next feature, another feature I wanted to present, is the stage construction analysis. So we do this via the element birth feature. So elements are born, giving rise to the next stage construction stage. It's a nonlinear analysis because forces and stresses are locked in from one stage and carried forward to the next construction stage. We can apply this to any structural type, and any analysis type, whether it's static, dynamic, model, or backlink, can be performed on completion of the construction stages. So this could be another import from STAAD.Pro, and then we can set up our stage construction analysis in Adina. Following on with cable state structures, I want to present that this cable and cable dynamics capability. Nonlinear cables can be modeled in any structural scenario, combined with any other element type and any other form of nonlinearity. And if you see quite closely at those red cables, you see that, well, they go from being slack to being tense as we apply the pre-stress to the structure. And then, for instance, using the analysis switch that I mentioned before, once we've completed the static analysis, we can perform modal, static, or dynamic analysis. If you think of a guitar chord, if we want to change the sound of a guitar chord, what we do is to change or modify the tension of that chord, right? Because then what happens is that the stiffness changes, the natural frequency changes, and that's how the sound of that guitar chord changes. So this is what happens on a cable state structure. The natural frequencies and the dynamic response will depend or will be certainly affected by the stress on those cables. And this is the stress stiffening effect that we capture. Again, this is useful for all kinds of cable state structures. Well, this one here is just a combination of the previous two. At the end of the construction stage analysis of this bridge, we see on the left-hand side how that cable is snapping from the top of the tower, which is unlocking the dynamic response of the bridge, of the towers, of the deck, and that requires a nonlinear time history analysis and cable behavior. And to the right-hand side, we see the how the cable springs back as a result of the stress when it snaps from the top of the tower and the shape that it takes. And one last example on cable and cable dynamics is this suspended pedestrian bridge, very wobbly and sensitive to dynamic excitation. So again, we can obtain the natural frequencies, decide whether those frequencies could match the pedestrian excitation, and this could lead to resonance or excessive vibration. And ultimately, well, we can also run traveling loads on top of the bridge that we can make, well, sinusoidal, constant value. We have really a range of possibilities. And of course, we can measure from that bridge accelerations, decide if they are excessive or not, displacements, as well as internal forces on the structure. Blast is something that is, well, certainly caused an interest to people. So I wanted to present this because for certain blast scenarios, codes of design like, well, UFC or the design of blast-resistant buildings for petrochemical facilities provide pressure time histories that can be applied usually as a function of the equivalent TNT mass or the standoff distance. And we can follow this approach in some cases where, well, we have there is no obstacles between the detonation and the structure, and those graphs can be calculated using the codes of design. In those cases, we're talking about structural nonlinear time history analysis, potentially with, well, could have large displacements, material plasticity, but we certainly don't model fluids. If we are in a, for instance, internal explosion inside the facility, there is lots of wave reflection going on. We may require other methods like computational fluid dynamics, but this is not a topic for today. It's just to put things in context. Following on with blasts, well, clients and asset owners often will specify or agree with an engineer the level of damage that they are willing to have in their structures in the event or in a blast event. Sometimes they may not want to have any, or at least not any significant permanent damage, but that's an expensive approach. So it's common to accept some level of damage on the structures while protecting the lives inside the building, so the building shouldn't collapse on top of the people inside. So different analysis techniques and different levels of sophistication may be required. This is an example of a model. Actually, this is a STAAD.Pro model within the installation kit that was taken all the way to a blast analysis in Adina. So we see we have a initial pressure applied to these columns. Is going to be very high intensity and short duration, and is going to cause the dynamic response of the structure. Of course, this is linear elastic. On this example, however, we see again these pressures here to this side of the building structure. Again, will be very short duration, like very few milliseconds, very high intensity, and we're going to see that these columns fail as a result of that, but we're going to see what happens to the rest of the structure as well. So we see how, as columns can't really cope with the vertical weight because the first row of columns is failing, that is distributed, is transferred to the next columns that continue to fail and buckle. So that progressive failure is something we capture in. Of course, from this model, we can obtain the plasticity, the ductility demands as a form of, for instance, we can measure the rotations and so on, as well as, the typical results we would want to obtain from a structure like this. But certainly, plastic strains and the angle of rotation, and we can compare those to the acceptance criteria or the criteria defined for that structure. And of course, we've seen collapse at the beginning, and if we want to see the footprint of the structure, how it fails, or evaluate the very ultimate capacity, we can model collapse as well, and the contact with the ground and between floors, and so on. This is a very simple example on how to use element mix when we have, for instance, some local loss of thickness due to corrosion or localized damage. So we could have modeled everything very much in detail, but in this case, we have this simple frame structure that could come from STAAD, and then in Adina we can locally modify that and refine it a little bit with different types of elements. And that allows us to capture things like local backend analysis and in turn the effect that has on the global behavior of the structure. On this one, for instance, to the right, what I did was to reduce the thickness of that pipe at the middle to model, for instance, the effect of corrosion locally, and we see how the structure is actually failing there. So we achieve this by this elements mix by what we call spider elements. So we have a beam that could come from the STAAD.Pro model. It's a usual normal beam element, and here we have something more detailed like shells, and we can connect both things together, and this is a fairly easy process. Okay, so we are getting towards the end of these features. This is the potential base fluid elements that I was speaking about before, and in my opinion is one of Adina's greatest and best kept secrets. Is a very easy to implement and computationally efficient element type, so the analysis run quite fast. It comes with a structures module, so it's not computational fluid dynamics, and we can capture hydrostatic and hydrodynamic effects in certain scenarios. We won't be able to capture very turbulent, very complex fluid phenomena, but certainly when we have a tank subject to, of any shape, subject to an earthquake excitation, this is something we can analyze. That graph to the top right of the screen is a comparison, so we're trying to measure the maximum height of the wave as the earthquake excites the tank, and we are comparing computational fluid dynamics, which is this one down here, with the potential base fluid element approach, and we see that the maximum height is being captured very accurately. Of course, we can evaluate the structure analysis as well of the tank and see how it performs in terms of stresses and so on, and forces. This is the tank using the potential base fluid element subject to the earthquake excitation, and as I was saying before, is really easy to implement. All we do is we model the fluid as a volume, we mesh it with fluid elements like if it was a solid, and we apply a fluid material property that will just have the density and the bulk modulus. So it's quite straightforward. And then the soil structure interaction capability in Adina. This is the last feature that I'm going to present today in terms of things that, well, are convenient features for models imported from STAAD. So Adina's material library includes geotechnical material models, and Bentley has products like Plaxis as the go-to for geotechnical analysis. But when a model, an analysis needs to have both the Crown's effect and also complex structural behavior, such as nonlinear statical dynamic, well, Adina offers the tools for a good comprehensive soil structure interaction analysis. In addition to those material models, well, we have the possibility to use compression-only springs for statical dynamic, and also to use springs and assign nonlinear PY curves if we have piled foundations. Right, and finally, the bolt preload feature. This is not something, perhaps that type of structure is not something we would import from Adina, but it's being reported as a, well, very useful feature, so I wanted to mention this as well. In Adina, the bolt preload is taken care of by means of, well, special bolt iterations, where the target preloads and sequence are specified by the engineer and automatically handled by Adina. If you look at that bracket, that simple connection to the right-hand side of the screen, we see how the top bracket is deflecting due to the preload on the bolt. So when we assign a tension to that bolt, the structure will deflect, we'll have elastic shortening, and automatically we'll lose some of the preload. So we have to preload it again until we reach the target. So in Adina, we don't need to do that. We just specify the target preload, the final preload that we need, as well as the sequence if we have many bolts on the structure, like the one, that connection to the left-hand side. So if we consider, for instance, this base plate, which is bolted to a concrete plinth and is subject to a separating load, for instance, a bending moment, if we look at the graph, which is right after that, and again, we consider two scenarios, one where we have the bolts preloaded and one where we don't have the bolts preloaded. As I said, that base plate is subject to a separation force. So if we look at the blue graph, which is the preloaded bolt, as the separation force kicks in, we are going from a bolt preload tension, but we see how that delta sigma is not very big. So as the separation force kicks in, the increase in stress of that bolt is not very significant because most of the preload, most of the separating force is being invested in decompressing or undoing that preload. On the other hand, the red curve is not preloaded. So what happens is that we start at 0 volt tension, but as the separation force starts to act, all that force is being invested in stretching the bolt. So by the time we get to the preload loss region, both have the same level of tension, but of course the delta sigma, the increase in tension in stress of the preloaded bolt is significantly smaller than the non-preloaded bolts in. So that is why we preload things when we want to limit or prevent fatigue. And to do that, well, we need certainly contact between surfaces and the bolt preload feature. Ultimately, we create a bolt force function like the one you see to the right, and that will allows us to inform fatigue design of bolts and rods. Okay, so we are almost at the end. So I'm going to be running now an example of a nonlinear backlink analysis. Just to prepare you, what we're doing in this process is to run a linearized backlink analysis first. That is the Euler backlink analysis, and we use that to introduce an initial imperfection to our nonlinear backlink analysis. So let's start with it. As usual, we are in STAAD.Pro, we have a simple frame structure. We're going to File, Export, and we're going to export the Adina input file as we've done before. We switch to the vertical axis Z, and the Adina input file has just been created. And now from Adina, as usual, go to File, Open Batch. We locate that input file we've just created from STAAD. So that's the structure there. We're going to set up a linearized backlinks analysis, as I said before, and we're going to request 5 backlinks modes. We will only be interested in the first one anyway, but it's good to look at more modes of backlinks. We need to, it's just a one-off box tick there. We need to set up large displacements to run linearized backlinks analysis. And we're going to work on the plane of the screen. So we're going to make this analysis 2D. We're getting rid of some degrees of freedom, so we don't have modes of backlinks outside the plane of the screen. And finally, we're going to add some loading to the top of the structure. So I'm going to pick 3 nodes. I'm going to set up a load type in the Z direction, which is vertical. And it's going to be negative values because we want that load pointing downwards. So with that, we set up the linearized backlinks analysis quite quick. So we're going to save the model. We're going to give it a meaningful name, for instance, 01 linear backlinks analysis. And we are ready to solve. That's going to be fairly quickly. We have the converge solution, so now we can change to the post-processing screen where we can visualize the results. So that is the first backlinks mode. As before, we can customize colors as we like. We see that it's a sway backlinks mode and it has a factor of 1.766 associated. So we make note of that. It makes sense to have the first backlinks mode being the overall sway of the structure. I'm going to refine the deformed shape of those beams, and we're going to look at other modes of backlinks as well. So load factor of 2, load factor of 3, 4, and almost 5. But we are interested in this particular backlinks mode, 1.766 load factor. So we go back to our original model, to the structures interface. And I'm going to, we're displaying the supports, the loading, and we're going to save this model with a different name. So we're going to create a copy. Again, something like 02 nonlinear backlinks might be a good idea. Now, as I said before, what we run for nonlinear backlinks analysis is static analysis with large displacements, which we already have in our analysis. And we're going to set up a time function. So it's not a dynamic analysis, but we work in time domain. So we're going to ramp up the loading from 0 to 3 to a load factor of 3. We know that by the time we get to 1.7, something will happen. And we're going to have 300 time steps, fairly small, 0.01, so that we capture that displacement in detail. We're now going to define, finally, that imperfection. We said that we were interested in mode 1. And what we do is we pick one node on the structure and we scale that mode of backlinks by an appropriate amount of imperfection. So we, in this case, defining 2 inches in the X direction, and that's how we scale up the whole mode shape for this analysis. When we press solve, we need to inform Adina where the linearized backlinks mode results are, and that's it. It's always the same and will apply to any type of structure. So analysis is running quite quickly, and by the time we get to 1.766, we know something is going to happen, and actually at just before 1.74, the structure has The analysis has failed to converge, probably because the structure became very strongly nonlinear. And there we go. So by one factor of 1.7338, we can see that the structure is having very large lateral displacements. Again, I'm going to refine a bit the shape of those elements. And this is exactly what we were expecting. So if we start to look at the time steps, which correspond to the different load factors, we only have vertical loads. And we see how, as we approach the 1.766 factor, the structure starts to deform laterally more and more, up to the point where, well, that is the last converged increment. Finally, to conclude with this, we're going to plot the displacement time history of one of the nodes. For instance, I'm going to pick one node at the top right of the structure again, and we're going to graph that displacement time history. We want displacements in X in the horizontal direction, in the horizontal, axis of the graph. And on the vertical, I'm going to put the time, which in this case is same as the load factor, because we have a one-to-one relationship. And we see how we never reach the 1.766. What happens is the structure starts to drop its stiffness drastically as we get closer to the backplane load factor, which is exactly, that is the equilibrium path we expect for a structure that has, is suffering global backplane analysis. Okay, so just as a recap, this is the process that we followed. First, we imported the model from STAAD.Pro to Adina. Secondly, we ran a linearized backplane analysis, and we made a note of the load factors and mold shape of interest. Then we set up a nonlinear static analysis with an initial imperfection from the linearized backplane analysis. And finally, we ran that nonlinear static analysis to get the overall backplane response of the structure. Of course, there is no limit to the type of backplane analysis that can be performed and type of a structure. We've seen the local backplane on the element mix case. We've seen the global backplane analysis, the behavior on this particular example now, and also when we showed the blast example, we also saw some columns, member columns backplane.